Okay, so welcome to the next video for Math 1560, Calc 1 at U of L for fall 2017. In the previous video, we saw how to calculate the derivative of inverse sine function of arcsine. And we actually saw a surprising result, right? Let me just remind you on the cover here. The derivative of our inverse trig function, sine inverse of x, right? You might expect an answer that somehow involves trig functions or inverse trig functions, right? Like derivative of sine was cos, the derivative of cos was minus sine. We expect maybe we should get something similar here, but we don't. The derivative of an inverse trig function is actually an algebraic function, 1 over the square root of 1 minus x squared, right? Which should be quite surprising, right? What does a square root have to do with an inverse trig function? But there it is. And now we're going to look at the inverse tangent function, and we're going to see that a similar story arises there. Okay, so just like with sine, in order to define an inverse for the tan function, we have to first restrict the domain because the tan function is not one-to-one, right? Here's what the graph looks like, right? It keeps repeating over and over and over and over again. And so we obviously don't have a one-to-one function, but if we choose one of these pieces that keeps repeating, and in particular if we choose this one that passes through 0, so we get those first quadrant angles between 0 and pi over 2, well, then we do get a one-to-one function, and if we take that one-to-one function and we reflect across the line y equals x, we get the inverse tan function, right? So notice that the inverse tangent function, the arctangent function, domain is all real numbers. The range goes from minus pi over 2 down here to plus pi over 2 up here, okay? So this is how we define the inverse tan function, okay? So again, we have this condition that saying y equals arctan x is the same thing as saying that tan of y equals x, with this additional condition that among all of the various y values that might satisfy this equation, we have to take the one that lies in this interval. Okay, so we're going to use that to calculate the derivative, right? We're going to use this relationship here. So last time we tried to tackle this using implicit differentiation. This time let's think of this more as a chain rule problem, right? So we let g of x equal arctan of x. Of course, you guys have probably caught on by now that implicit differentiation and chain rule are really the same thing, so there are no surprises there, but let's do it this way. So the derivative of tan of g of x is equal to the derivative of x. So remember that the derivative with respect to u of tan u is secant squared u. Okay, so what do we get for this derivative on the left hand side? We get secant squared, my u in this case is g of x, and then I have to multiply by du dx, which is g prime of x, which is exactly the thing that we want to calculate. And on the other side, derivative of x is just 1, so therefore g prime of x is 1 over secant squared of g of x. Okay, so that's an answer in terms of x, but it's not very satisfying, right? Because it's sort of, it still references this function g of x, secant squared of arctan of x. Can we make this any simpler? Well, let's note that, one of the variants on sine squared plus cos squared is that 1 plus 1 plus tan squared theta is equal to secant squared theta. That's one of our identities. So if theta is equal to g of x, right? And so notice, and also what do we know about that? Well, we know that tan theta then, tan of g of x, what is tan of g of x? It's sitting right here. It's x. Okay, so what do we get? We get that secant squared theta, secant squared g of x is 1 plus tan squared theta, but tan theta is x, so 1 plus x squared. So 1 over 1 plus x squared. That's the derivative of the arctan function. Okay, we've got two of them out of the way. We'll do one more and we'll call it a day.